Hi everybody. In this video we are going to discuss the Bodeplot, which makes it possible to analyze systems in the frequency domain using a graphical method. Well, let's start off with an easy example, an RC network, which has been depicted over here, consisting of a resistor R1 and a capacitor C1 over here. And we want to know the relationship, the transfer function between the output voltage U out and the input voltage U in. We can do that with the voltage division rule, which says that the output voltage is equal to the impedance of the capacitor divided by the resistor plus the impedance of the capacitor, and that times the input voltage. So we get the impedance of the capacitor, which is 1 over j omega C1, divided by the resistance R1 plus the impedance again from the capacitor, which is 1 over j omega C1. Well, now we can multiply the numerator and denominator with j omega c1, and then we get 1 here in the numerator, and here we get j omega r1 c1 plus this becomes 1. And that is my transfer function for this system. Well, we are going to draw the Bodeplot, and as you should know is that the Bodeplot consists of two separate plots, which is the Bode amplitude plot and the Bode phase plot. Before we start, you should know that when we apply an AC signal to a system which is frequency dependent, like that RC network, we get to the output for every single frequency an output signal with a different amplitude, A2 in this case, and with a different phase angle related to the input signal over here. So what we are going to do in the Bodeplot is we are going to plot two things. We are going to plot the amplitude and we're going to plot the phase. So how do we do it? Well, we have two plots and we plot on the horizontal axis the omega, so the radial frequency which is over here and over here, which is of course the same for the input and the output signal. We plot that in a logarithmic way, which means that we don't have equal distances between the numbers on the horizontal axis like 1, 2, 3, 4, 5, etc. But the distances between 1 and 10 is equal to the distance between 10 and 100, which is equal to the distance between 100 and 1000, and so on. That is a logarithmic axis. That is what we are going to do for both plots, both the amplitude plot and the phase plot on the horizontal axis. Now let's look to the vertical axes. For the amplitude plot, we don't plot the relationship between A2 and A1, so between the amplitude of the output signal and the amplitude of the input signal, but we take the logarithm with base 10 of that division of A2 and A1, and we multiply it by 20. And the unit of that amplitude plot, the unit of this calculation is dB, decibel. In the phase plot, we are going to plot the phase, which is the argument of the function for every frequency. Well, let's look in more detail. Well, this is our system, consisting of the transfer function which we have derived earlier, which is 1 over 1 plus j omega times r times c. Now let's look to the amplitude plot. What we do when we calculate the amplitude of this system, we take the amplitude of the numerator and we divide that by the amplitude of the denominator, which means that for both the numerator and denominator, we take the square root of the real part squared plus the imaginary part squared. Now let's look to this function. What does that mean? Well, in the numerator, we have only the number 1, which is a real number. So we can say directly, hey, the amplitude is always 1. You can also calculate it by doing this mathematical trick, this mathematical calculation, which says it's the real part squared, which is 1 squared, plus the imaginary part squared, which is 0 in the numerator. and then take the square root out of it, which is the square root from 1 squared, which is square root of 1, which is 1. That's the one over here. For the denominator, we do the same thing. We take the square root out of the real part, which is 1 squared, which is over here, plus the imaginary part, which is everything in this part besides the j. So it's omega times r times c, and that part squared. And then we take the square root out of it. So that is the amplitude. The phase is the argument of this function, which is the phase of the numerator minus the phase of the denominator. Well, let's start with the phase of the numerator, and then we go on with the phase of the denominator. And for both numerator and denominator, we can calculate it by taking the arctangent, or the inverse tangent, the tangent inverse, different name for the same mathematical operation, between the imaginary part divided by the real part. Well, let's start with the numerator. Well, this is only a real number, so when you look to it in a complex diagram, it's on the real axis, so I could say on forehand that the argument of this numerator is 0. But I can also calculate it by using this mathematical expression, which says it's the arctangent of the imaginary part, which is 0 in the numerator, divided by the real part, which is 1. So I get the arctangent from 0 over 1, which is arctangent over 0 over the arctangent of 0, which is 0, which is 0 over here. From the denominator, we do the same thing. So it's we said earlier, it's the phase of the numerator minus the phase of the denominator. So we get minus the phase of the arctangent of the imaginary part, which is omega times r times c, divided by the real part, which is 1. So we get minus arctangent from omega times r times c. So now we have two expressions for the amplitude and for the phase. And now let's put them in a way that we construct the Bode diagram. This was my amplitude and this was my phase. And what we can see over here is that we often consider this in this RC network as our time constant tau. So we can replace this r times c by tau, which makes it somewhat more easier to see. So the phase is now minus r tangent omega times tau. We're going to look to three essential points for drawing the Bode amplitude plot and the Bode phase plot. We're looking to frequencies, radial frequencies, which will be very small, so end up to 0. We are going to look to frequencies which will be very high, so ending in infinity, and we are looking to so-called crossover frequencies. Well, how do we do it? Let's use this table with this information, and we start over with these three situations for omega. Let's start with omega is very small, almost 0. When omega is almost 0, this part is almost 0, and then we get for the amplitude, it's 1 over square root of 1, because this is 0, which is 1, which stands over here. For omega is infinite, which is standing over here, then we fill in a very large value for omega. So the denominator becomes very, very large, which goes to infinity. And then we get an absolute value or an amplitude, which is 1 over a very large number, which goes to 0. So for infinite numbers, infinite frequencies, my amplitude will be 0 or will go to 0. At this special point, which we call a crossover frequency, which is 1 over tau, we get a special situation. Well, how do we come to this crossover frequency? Well, the crossover frequency is the value of this omega, in which the imaginary part, so everything besides the j, is equal to the real part. Well, the real part is 1, so omega times rc has to be 1 as well. So in that case, omega is 1 over rc, or 1 over tau when we call RC the time constant tau. So the crossover frequency in the system is 1 over RC or 1 over tau. Well, in this situation, when the crossover frequency omega is 1 over RC, we can fill it in over here, and then we get 1 over RC times RC, which is 1. 1 squared plus 1 is 2, and then the square root out of 2 gives us a total amplitude of 1 over the square root of 2. And we can write it in another way. We can say, well, 1 divided by the square root of 2 is equal to 0.5 times the square root of 2. So for the amplitude, we have 3 essential points, and we have the amplitude at these special frequencies. Omega is very small, omega is very large, and the crossover frequency. But we have seen that we want to use the logarithmic function of the absolute value for drawing the Bode amplitude plot, and we are also going to multiply that by 20. And when we do that, we can derive, based on the values over here, the corresponding values for the Bode amplitude plot. Well, 20 times the log of 1 is 20 times 0, which is 0 dB. Well, when the h will be very, very small, we get 20 times the logarithmic function of a very, very small function, which will be minus infinity. Multiplied by 20 is still minus infinity, so a very large but negative value. And on my crossover frequency, we've seen that the amplitude is 1 over the square root of 2, or 0.5 times the square root of 2. And when we take the log of it, so the logarithmic function with base 10, and we multiply it by 20, we get minus 3 dB. So these are the points at these frequencies in my Bode amplitude plot. Now let's look to the phase. Well, this is the expression for the phase. For omega is 0, we get a phase of minus arctangent of 0, which is 0 degrees. At very, even going to infinite numbers for omega, very high numbers of omega, so going to infinity, we get minus the arctangent of a very large number, which goes to minus 90 degrees, which is over here. And at the crossover frequency, so at the point where omega is 1 over tau, we get minus the arctangent of 1 over tau times tau, which is minus arctangent of 1, which equals minus 45 degrees. So now we have 3 essential points which can help us when constructing the Bode plots for the Bode amplitude plot and the Bode phase plot. So what are we going to do? Well, when we are going to draw the Bode amplitude plot and the phase plot, we are going to use asymptotes, because we are not interested in exactly the correct numbers, but we want to know, when we are using this technique for designing electrical circuits or control diagrams, control systems, these kind of things, we want to know what the behavior is. So we are going to use asymptotes. And as I said, on the horizontal axis, we are going to use the frequency on a log scale. So at equal distances, we have equal distances of 1 to 10, 10 to 100, 100 to 1000, etc. We have, at these values, we have the equal distances. An increase, that's also important, and something you should know, an increase by 10, we call that a decade. So when we increase the frequency from 1 to 10, we call that a decade. And when we increase the frequency of 10 to 100, it's again a decade. And from 100 to 1000, it's a decade. And all these decades have equal distances on the horizontal axis. Well, let's start with the Bode amplitude plot. We have defined a crossover frequency, and that crossover frequency, at that point, the low frequency behavior merges into the high frequency behavior. So that is an important frequency. Another thing which is important is the slope of my Bode amplitude plot in this particular example at higher frequencies. Well, what happens when omega is very large according to this crossover frequency? Well, when omega tends to go to infinity, then we have, this was my expression for the amplitude, we have 20 times the log of 1 over the square root of 1 squared plus omega times RC times R times C squared. When omega goes to a very high number, we can neglect this one. So this one doesn't matter anymore because this part will be much higher than that part, so we can neglect it. And then we have a situation that we can get a more easier expression for the absolute value for high frequencies. Because what's left is then that we have 20 times the logarithmic function of 1 over omega times r times c squared, and then the square root out of it, which brings us 20 times the logarithmic function of 1 over omega times r times c. And what you see now is when at very high frequencies, so at frequencies higher than the crossover frequency, when my omega changes or increases by a factor of 10, then this expression will be 10 times lower. So when omega gets 10 times higher, this complete expression will be 10 times lower because the omega is in the denominator. So when this will be 10 times lower, this means that 20 times the log of 10, which is 20 times 1, which is minus 20. So at every increase by a factor of 10 of this omega, my amplitude in dB will decrease minus 20 dB. So it will get 20 dB lower compared to a frequency which was 10 times lower. So every time the frequency is increased by a factor of 10, frequency is higher than the crossover frequency, the amplitude will be 20 dB lower. So we call that a decrease of minus 20 dB per decade. Now the phase plot, how are we going to draw the phase plot? Well, we start over with the crossover frequency, and of that, at that crossover frequency, we have seen that the phase is known because it was minus 45 degrees in this case. And because we're drawing the asymptotic behavior, we draw a line starting at 1 over 5 times this tau, so a frequency which is 5 times lower, and we define a point which is 5 times higher, and between these points we draw a line from the low frequency behavior to the high frequency behavior. It's a lot of information. I can imagine that you are a little bit confused, so let's start with an example. So we have an example over here in which we have a transfer function which is equal to 1 over 1 plus j omega times 0.5. So the first thing we know is that we can define the crossover frequency, because the crossover frequency is the frequency in which the real part over here is equal to the imaginary part over here. So when 1 equals omega times 0.5, it results in a crossover frequency omega, which is 1 over 0.5, which is 2 radians per second. So we have that crossover frequency here, 2 radians per second. Why is it over here? Well, let's have a look. This is a frequency of 10 to the power minus 1, which is 0.0 radians per second. This is 10 to the power of 0, which is 1 radian per second. This is 10 radians per second, and this is 10 to the power of 2, which is 100 radians per second. So this is the frequency in radians per second, and what you see over here is that the distance between every decade, so every increase of frequency by a factor of 10, is equal. So here we have 10 to the power of 0, which is 1 radian per second, and this is 2, this is 3, this is 4, 5, 6, 7, 8, 9, 10. So 2 is over here. Well, when this is 10, this will be 20 radians per second. So not 11 or something like that. This is 10, so this is 20, this is 30, etc. Keep that in mind. So back to my crossover frequency, which was 2 radians per second. And we said this is 1, so this is 2. So here is my crossover frequency. Well, for very low frequencies, um, this part will be very low, so the amplitude, which we have seen, goes to 1 over 1, and my amplitude in dB is 20 times the log of 1, which is 20 times 0, which is 0 dB. So we start over with 0 dB. And that goes up to towards the crossover frequency, and from that crossover frequency on, we see that the amplitude drops by 20 dB per decade, which is written over here, which we have seen in the calculation on the previous slide. So the amplitude behavior, the characteristic, is the red one. And notice that it's not exactly the correct Bode amplitude plot, because that is the blue one. And you see, especially here at the crossover frequency, a difference of 3 dB. So the real Bode amplitude plot is 3 dB lower than what we draw from our asymptotic behavior. But what I mentioned before, by drawing the asymptotic behavior, we get a very good impression of the behavior of that system for low and for high frequencies. Well, that's the Bode amplitude plot. For the Bode phase plot, we have seen that for low frequencies, the phase is 0 degrees. For high frequencies, in this example, the phase is minus 90 degrees. At exactly the crossover frequency, which is here, we have calculated that the phase is minus 45 degrees. So now I'm going to construct the phase characteristic by taking this cutoff frequency of 2 radians per second, and we divide it by 5. So 2 divided by 5, 2 over 5 is 0.4 radians per second, which is here. Well, because it is 0.1, 0.2, 0.3, 0.4 radians per second, here, this point, and we draw a dot, or we put a dot at 5 times the crossover frequency, so it's 5 times 2, it's 10 radians per second, which is over here. And between these values and the phase at the crossover frequency, we draw a line from the low frequency behavior, phase behavior, which was 0 degrees over here, towards the high frequency behavior over here. And then we get the asymptotic behavior of our system, so the phase behavior of a system, which is put over here. And you can also see that we again make an error compared with the real phase behavior, which is the blue line. But again, it gives us a very good impression about how this system reacts and how it's functioning in practice. So that is the Bode amplitude and phase plot construction. Now let's look what happens if we put 2 or more systems in cascade or in series, as you could say. Well, we have a system H1, and behind that system we put another system, H2. What we are going to express, what we are going to learn, is that it will be very easy to draw the total Bode plot of the combination of these systems, because we are going to make use of complex about we're going to get we're going to get you to use complex behavior rules. This system H1, but also this system H2, are complex numbers. It's an expression, it's a transfer function put over here, but we can also write it as a complex number. And when we do that in the Euler notation, we get this complex number for system H1 and this complex number for system H2. So H1 is a absolute value or an amplitude R1 in this case times e to the power j phi1, and phi1 is the phase of this system. And for system H2 it's the same expression with an amplitude of R2 and the phase here in the power of e, which is phi2. Well, when we apply the rules of the mathematics of working with numbers with powers, we can say that the total system, which is the multiplication of h1 and h2, is equal to this expression times that expression, which gives us r1 times r2 times e to the power, and then we may add up the phases v1 and v2 times j. So what we can see in the first place is that the phases are added to each other. What does that mean with respect to the Bodeplot? Well, when we put two systems in cascade or in series, we may add the phase plots. So that is quite easy, because when we have a phase plot of this system and the phase plot of that system, we can add them up, and that is of course much more easier than analyzing complex system. Well, this is another point. For the amplitude, it says R1 times R2. But we are not drawing in the Bode amplitude plot the real amplitude, but we are taking the log, the 10 base log of this function, the logarithmic function of this, and multiply it by 20. And when we do that, we see that we get 20 times the log of the system, which is 20 times the log of this complete expression, or in a general way, 20 times the log of h1 times h2, absolute value, which indicates we are talking about an amplitude, which is 20 times the log of this function plus 20 times the log of this function. So we can add the Bode amplitude plot of this system towards the Bode plot of this system, the Bode amplitude plot of that system. So we can also add both amplitude plots. And why is it possible? Because this was the mathematic rule we applied. Log A times B is log A plus log B. So what we have seen is, by using this expression for the Bode amplitude plot, we may both add the phase plots of the different systems, and we may add the amplitude plot of both systems in the Bode amplitude plot. Well, yeah, this is what I mentioned for the phase plots. So let's do it in an example in which I have two systems, which are almost the same systems as I analyzed before, only the crossover frequency of both systems are not equal to each other. They differ. So, well, let's analyze this system. There are a lot of lines in this figure. Don't worry, I'm going to analyze it with you. From this system, we have seen that we can calculate the crossover frequency. For calculating the crossover frequency, we can set the imaginary value over here, everything besides the j, which is omega times 0.5, and we set that equal to the real part. So omega times 0.5 is equal to 1. So omega crossover frequency is 1 over 0.5. It's 2 radians per second. Doing the same for this circuit gives us a crossover frequency of 1 over 2, which is 0.5 radians per second. Well, these are systems which you analyzed before, but we see in this system that from the blue system we have a crossover frequency at 0.5 radians per second. Well, where is it? This was 10 to the power minus 2. This is 10 to the power minus 1. So this is 0.1. This is 10 to the power 0. So that is 1. So it's somewhere between this and this frequency. This is 0.1, this is 0.2, 0.3, 0.4, 0.5. Hey, here we have our crossover frequency for the blue curve. For the green curve, the crossover frequency is 2. Well, this is 10 to the power 0, which is 1. This is 10 to the power 1, which is 10. So 1, 2. So here's the crossover frequency for the green system. So at the green system, my crossover frequency, which is at 2 radians per second, indicates the point where the low frequency behavior changes into the high frequency behavior. So until this crossover frequency, we have seen that the amplitude was 1. So 20 times the log of 1 is 20 times 0, which is 0 dB. Again, for low omegas, we can neglect this, and we have 1 over 1, which is 1, 20 times the log of 1 is 0 dB. And because this is what we call a first order system, we have only one j omega and not j omega squared or j omega to the power 3, etc. We have calculated that from the crossover frequency and further on, this slope decreases with 20 dB per decade. So this is minus 20 dB per decade. That's the amplitude. For the blue system, we have the same thing, only the crossover frequency changes or is changed to 0.5 radians per second, which is over here. So again, it starts with 0 dB, and from the crossover frequency, it declines with minus 20 dB per decade. So when you want to draw the Bode plot, the Bode amplitude plot of both systems in cascade or in series, we can add up the green system and the blue system. So 0 plus 0 gives us an amplitude of 0 in total over here. Then my blue system starts to drop. So my combination of the blue and the green one starts to follow this blue line because the green one still stays at 0 dB. And from this crossover frequency and higher, the green characteristic is also declining. So then we get that a steeper slope over here, which is not minus 20 dBs anymore, but 2 times minus 20 dB, which is minus 40 dB per decade. So this is the red amplitude plot, which indicates both the amplitude plot of the combined system, consisting of 2 crossover frequencies, one over here due to the blue system and one over here due to the green system. And it ends up with minus 40 dBs per decade, because now we have 2 first order systems in cascade. For the phase, we can do an analysis which is more or less equal. Well, at the crossover frequency of this system, which was 0.5 radians per second, which is over here, we know that the phase was minus 45 degrees. And we can draw a line between the crossover frequency divided by 5, which is 0.5 divided by 5, which is 0.1 over here, and the frequency of 0.5 times 5, which is 2.5, which is somewhat higher than 1, of course, but somewhat lower than this one. This is 2. So it's 5 times this, somewhat higher than 2. So this is 5 times 5 times 0.5. It's 2.5, which is somewhere here between 2 and 3. So these are the points from my phase characteristic. We know that the phase for low frequencies is 0. We know that the phase for high frequencies is minus 90 degrees. So we now construct the Bode phase plot by drawing a line from this frequency through the cutoff frequency to the frequency which was 5 times higher, which was over here. And then we have the Bode phase plot of the blue system. Well, we can do the same thing for the green system. The crossover frequency was at 1 over 0.5, which is 2 radians per second. This is 2 over 5, which is 0.4 radians per second. And the higher frequency was 5 times 2, which is 10 radians per second, which is over here. They start also at 0 degrees for low frequency, and they end up at minus 90 degrees for high frequency. We construct the green Bode phase plot for the system, and now we have 2 phase plots for the green and the blue system. Well, the combined phase plot of the total system in series or in cascade is the red one, which we can construct by adding the green one and the blue one. Well, let's do it. Both curves start at 0 degrees. Adding them up, we get 0 degrees. Then the blue phase starts to drop, so the red one follows the blue line. Then the green plot comes into action. Well, here the blue one stays at minus 90 degrees, and at this point the green curve also ends at minus 90 degrees. So the total combination ends up at 2 times minus 90 degrees, which is minus 180 degrees. So quite easy by drawing the Bode plots for both the amplitude and the phase for the separate systems, and then add up the amplitude plot and the phase plot. I have one example more. Suppose we have a more complex system, which does not consist of exactly the same systems, but a more complex way. What we have, for instance, over here, which says that we have a system, one system, which has a transfer function over here, which is 10 times 1 plus j omega times 0.2 divided by 1 plus j omega times 0.02. And we want to draw the Bode plot. Well, how could we do this when we have a more complex transfer function? Well, the solution is we are going to divide this system into so-called basic systems. And I put them over here. We can say, well, we split off the gain over here. We call that a basic system. We split off the numerator over here, which is this system, which we call a biased differentiator, and we split off the function 1 over 1 plus j omega times 0.02, which is the red system, a biased integrator. So we split up this combined system in 3 different systems, and we call this one H1, this one H2, and this one H3. And now we are going to do the same thing as in the previous example. We are going to draw the Bode plot, the Bode amplitude and the phase plot of this system, the Bode amplitude and phase plot of this system, and again of the red system. And then we add them all up, and we have the combined Bode plot of the real H system H, which was mentioned over here. Well, let's start off with defining the crossover frequencies. Well, the green one does not have a crossover frequency because there's not a j omega in this in this transfer function. The blue one has one because this is again a complex number with a real part and an imaginary part. And we've seen that we can calculate the crossover frequency by setting the imaginary part, which is everything besides the j. We set them equal to the real part. So 1 is equal to omega times 0.2. So the crossover frequency omega is 1 over 0.2, which is 5 radians per second, which is written over here. For the red system, we can do the same thing. Well, we have a crossover frequency due to this denominator over here, and that crossover frequency is 1 over 0.02, which is 50 radians per second. Well, we know that, and we can say that for this green system, this is only a gain. We can say, well, this is quite easy, this Bode plot, because this is a constant value which is independent of frequencies because there is no omega involved. So for every frequency, the amplitude is 10. So that brings us to 10 times the log of 10, which is 20 times the log of 10, which is 20 times 1, which is 20 dB. And the phase of system 1, H1, is always 0 because this is a real number, which is in a complex diagram on the real axis. So it's always on the real axis. So the phase is always 0. Can also calculate it by what we have done earlier in this video. We can say, well, it's arctangent of the imaginary part, which is 0, divided by the real part, which is 10, which brings us the arctangent of 0, which is 0. So for the green part, we have a constant amplitude line on 20 dBs and a constant phase line on 0 degrees. Well, we only have to analyze the blue and the red system. So let's do it. A lot of information again in this plot, but we are discussing it one by one. Well, we have the green system H1, the blue system H2, and the red system H3. We have calculated amplitude and the phase of the green plot, 20 dBs for all frequencies for the amplitude, and always for every frequency 0 degrees as a phase. We have defined the crossover frequencies for the blue system, which was H2. The crossover frequency is at 5 radians per second, which is over here, and for the red system, the crossover frequency was 50 radians per second, which is over here. Well, we can draw the amplitude plot of the blue system. For low frequencies, we can neglect the imaginary part, so we have an amplitude of 20 times the log of 1, which is 20 times 0, which is 0 dB. And we know that from a it's the blue one, this is the blue one. And from a crossover point, so at the crossover frequency, we know that this system will have a slope of plus 20 dBs per decade. Why is it a plus 20 dBs per decade? Because at higher frequencies, this amplitude is increasing because this is in a numerator. We can also say this is 1 plus j omega times 0.2 divided by 1. So we see this expression is in the numerator, and the amplitude is 1 plus omega times 0.2 squared, and then the square root out of it. So at higher frequencies, this amplitude goes up. And because it's a first order system, it's only 1 j omega, no j omega squared or to the power of 3, etc. It's a first order system, so it increases with plus 20 dB per decade, which is drawn over here. So the blue curve, the dashed curve, is the asymptotic Bodeplot of the blue system H2. For the red system, we have seen how that works in 2 examples, so I'm not going to discuss it in details anymore. We've seen that the crossover frequency is at 50 radians per second, which is over here. So it starts off at 0 dB, and from the crossover frequency it drops with minus 20 dB per decade. So, well, adding these amplitude plots of H1, H2, and H3 gives us the purple plot over here, in which this one is the asymptotic combination, which is the red one and the blue one. They start off at 0 dB, but the green one starts and ends up at 20 dB, so the combination starts up at 20 dB. Then the blue one increases from the crossover frequency over here with 20 dB per decade, so the combination, the purple one, also increases with 20 dB per decade. And then from this crossover frequency, this system, the red system, starts to drop with minus 20 dB, which compensates the plus 20 dB of the blue curve, so it ends up here at a constant value, which is 40 dBs when you calculate it. For the phase plot, there is a similar approach. Well, we have seen that for the green plot, the phase is always 0. From the blue plot, we see that for low frequencies, the phase is the arctangent of the imaginary part, omega times 0.2 divided by 1, so the arctangent of omega times 0.2. And when omega is very small, we get the arctangent of a very small number, arctangent of 0, which is 0. So we start off at 0. But for very high values of omega going to an infinite value, we get the arctangent of an infinite value, which is 90 degrees. So we end up at 90 degrees. And then we can construct the Bode phase plot for the system using the cutoff frequency, a frequency 5 times less and 5 times higher, and then we get the blue dashed line. Again, this line is the real line and the dashed line is the asymptotic line in which we are interested. For the red system H3, we have done that in examples before. We have seen that from the cutoff frequency at the cutoff frequency, the phase is minus 45 degrees. And for low frequencies, the phase is 0 degrees. And for high frequencies, it's minus 90 degrees. So now we can add up all phase plots, which gives us the purple phase plot, which is depicted over here. This is the real phase plot. And you can also do it by adding the asymptotic lines. What we see is for low frequencies, all contributions of H1, H2, and H3 are 0 degrees. So we start off at 0 degrees. And for high frequency, we see that the green phase is 0. We see that the blue phase is plus 90 degrees, and we see that the red phase is minus 90 degrees. So they compensate each other. So we end up also at 90 degrees. And in between, we see that the blue curve from system H2 is starting at a lower frequency than the red curve from system H3. So we see that the phase increases, and then when the red system comes into action, we see that the phase drops again up to the 0 degrees at the end. So well, how do you construct Bodeplots? Let's end with that. What is always good is to start up with splitting a complex function in a cascade system of basic systems. Then determine for systems which have a j omega in it, so which are not only a constant value, determine for these systems the cutoff frequencies. And when we have the cutoff frequencies, where we can draw the low frequency behavior and the high frequency behavior. We can do that for both the amplitude plot and for the phase plot. And we do that for every part of the system, so for every basic system. For the phase diagram, we know that what the phase will be at the cutoff frequency, at the crossover frequency, and then we can draw the complete phase plot by starting the phase plot at a frequency from which is omega divided by 5 or multiplied with 0.2, and it ends up with 5 times crossover frequency, and then we can connect that to the phase behavior for low frequencies and high frequencies. And when we do that for all basic systems, we can add all different plots together, and then we get one amplitude plot, one Bode amplitude plot, and we get one Bode phase plot of every system. Well, that's a lot of information, so please study this information quiet and easily. Thank you for watching, and I see you next time. Bye bye.